Okay, so last section is applications of nonlinear equations. The most important one we're going to do first, and that is the logistic function, which I think you did a little bit of in calc, but we'll go through it, derive the solution for it so that you guys have a way to approach these problems. But the idea here is that if you have population models where the rate of change varies proportionally with the current population, this may not be the most realistic. Especially long term. Okay, because usually there's some kind of limiting capacity. You hear about places being overcrowded and stuff like that. And I mean, you can kind of see what it looks like. A typical population model might grow exponentially for a while, but then it sort of starts to taper off. And I mean, that's the kind of graph that we're going to look at here. Okay, and the idea is that we start with the model 1 over p times dp dt equals a minus b times p. Okay, and I'll explain what this is. This left-hand side, you can think of that as the rate of growth per person. Okay, so if you multiply it by 1 over the population, the left-hand side is the rate of growth per individual. And now what we're doing here is assuming that to find the rate of growth per person, we simply look at birth rate, and the assumption here is that the death rate is proportional to the population. Okay, so we're calling the birth rate A, we're calling the death rate B, and we're saying that it's proportional to the population. And this is it's a little bit more accurate model long term if you look at it this way. Okay, so this is where we start with a logistic function. And if we kind of put it in the typical format, multiply through by p, we get dp dt equals p times a minus bp. Okay, so this is the logistic equation. And the solution to this is called the logistic function. Okay, so this is a logistic model of growth, which will usually have some sort of limiting factor as time goes on. So we like these models because they're usually much more realistic in the long term. All right, so let's go ahead and solve the differential equation so we can kind of look at the solution and see what we can gather from that. So if we separate variables, let's see, we get dp over, wanted to use black. We get dp over p times a minus bp, and that's going to equal dt. And now we reach a point where we can integrate, but we're going to have to use our friend partial fractions on the left-hand side to figure out how to integrate this. So let's look at 1 over p times a minus bp. What would the decomposition look like? So I'll use capital A. Okay. So then multiplying through by the denominator on the left, we get 1 equals A times little a minus little bp plus big B times P. And if we compare coefficients, let's see. We get that, I'll do little a, so this is the constant term, that has to equal 1. And now, there is no p on the left-hand side, and on the right, that comes from b minus little ba. Okay, so solving this, we want to find out what a is, capital A anyway. A is going to be 1 over little a. And then if I plug this in to here, we get b over a. So then big B is little b over little a. Okay, so a little tricky, but I mean it's not too much work. Now you can replace the numerators back here on the left-hand side, so what we're really doing is integrating 1 over a over p plus b over a minus bp, and that's all dp. We're still integrating dt on the right. Alright, integral of 1 over a. 1 over a is a constant. So we'll have 1 over a times natural log of p. And then, let's see here, we're going to get natural log of a minus bp.
Good morning, teachers. We are giving students a couple extra minutes to arrive to class, so if they arrive tardy, please allow them into your classes, and we will be also issuing tardy passes. Thank you.
Okay. Let's see. We have the b over a still out in front. And then to undo the chain rule, we have a minus 1 over b. And then on the right-hand side, we'll do t plus c. Alright, so if we clean this up, we get, well, this is not too bad. The b's will cancel out, we get minus 1 over a. So I'm going to multiply everything through by a. So now we have no fractions here. On the left we can combine the natural logs. So natural log of p over a minus bp will equal at plus ac. Exponentiate both sides, we get p over a minus bp equals e to the at times e to the ac, so I'll call that c1. Okay. And now the idea is to try to figure out what the population is going to be. So I can multiply through by the denominator. So I'll get p equals ac1 e to the at minus BP C1 e to the AT. And then I can factor out the population from these two terms and group it on the left-hand side. So if I pull out a P from this P, all I get is 1. If I add this term over and I factor out the P, I get B C1 e to the AT. And that's going to equal AC1 e to the AT. And now we can get our solution. P will be AC1 e to the AT, divide by that factor, 1 plus BC1 e to the AT. And now, I mean, this is fine. And I think the idea here, and I kind of get this, instead of having two exponentials, instead of having e to the AT and then another e to the AT, what we can do is multiply the numerator and denominator by e to the minus AT. So then what that'll do is give us just AC1 in the numerator, and then just give us one exponential in the denominator. I'll put the BC1 term first, and then it'll be e to the minus AT. Okay. Now, let's get some initial conditions in here so that we don't have the C1 in there. Because eventually we want to get to a point where, I know some of you came in a little late, but if we can model a scenario and it looks like this logistic equation over here, then what we want to do is be able to have a solution ready that we can kind of just plug everything into. Okay, so we don't want the C1 there anymore, but it'll be useful to have it in terms of the initial population. So, typically, they'll give you an initial population. And we can go ahead and replace that into the equation and solve for the constant. So we'll have P equals A times C1 over BC1 plus, and then if I plug in 0 for T, this is just a 1. So now we got to go back and find C1. It's going to be similar to what we did earlier. Multiply by the denominator. So you get PBC1 plus B equals AC1. Factor out the C1. You know what? Let me put it on the right-hand side. Sorry. Factor out the C1, so then we have A minus BP. Oh, hold on. One thing I forgot to do. If I'm plugging in 0, what should our population be now? There we go. Okay, so factor out a C1 minus B, and then this is just going to be P naught. Okay, so then C1 will be initial population over A minus B times initial population. Okay, now what we're going to do is take our constant, plug it into our solution, and go from there. So, let's see. Now we get the population will be A times C1, so P naught over A minus B P naught over BC1, so B times P naught over A minus B P naught plus e to the minus AT, and I'm going to go ahead and multiply by the denominators to get the complex fraction out of the way, and I think that's good enough. So we'll have A P naught over B P naught plus A minus B P naught e to the negative AT. And here's our solution. Okay, so you have a couple options. Well, you know what? Let's stop there for a second. I'm going to pose an example here, and then I'll explain what your options are. Because, I mean, you could theoretically just not know the solution and still solve it. It might take a while. But the idea is you can recognize if you model a scenario or a system and it looks something like this, and you know that the solution for that looks something like this, you can bypass all this partial fraction business and doing all that stuff that we did to get here. Now, it is kind of a lot to memorize, but you know, if you do it a few times, you kind of see the hang of it. So here's the example. Does anybody still need this part here? Okay. So let's say that the rate at which the flue spreads is proportional to the number of students X that are infected and not infected. So it's proportional to both those that are infected and those that are not. If one student is infected initially, how many are infected after 6 days if after 4 days 50 are infected in a population of 1,000 students? Sorry, I know that's a lot to write, but for those of you that peeked ahead at the practice packet and saw the BG infecting wheeling problem, this will be how you pretty much go about doing that. Okay. So let's see if we can model this. X is going to obviously be the number of students infected at time t. And we know that the rate at which people get infected, which is dx dt, is proportional to two things. It's proportional to what? Which is? And? Very good. So, this is the amount infected, and this is the amount not infected. Okay? And now we do have that the initial population that was infected is just one student. So x of 0 is 1, or x naught is 1, same thing. So here's our model. And now here's what I was talking about before. If you want, you can go ahead and just, power your way through the solution. which is possible. It's not horrible. It's just got quite a bit of work. Or if you already know that this looks like, so if we're going to use the logistic equation, we just kind of identify what piece is what piece, and then we plug everything in. So we're going to try to see what matches up here with our dP equals P times A minus BP equation. And we also know that the solution, which is P equals A P naught over B P naught plus A minus B P naught e to the minus AT. Okay, so we have a couple things here. A would be what in this equation? Almost. 1000K. Good. This model just has P times A. We have this extra constant in there, so that'll also get included. Does that make sense? B would just be what? Well, since the model are both minus, just K. So we have 1000K, we have K. Our P naught, which is actually X naught, is 1. Does that make sense? So plug it in. I'll use the actual X equation. So we'll do X of T is going to be 1000K times 1 all over B, so K, initial population 1, plus A, which is 1000K, minus B, which is K, times 1, all over, or I'm sorry, all times e to the negative 1000K, since that's A, times T. Okay, so if we clean this up a little, we have 1000K, okay. 1000 minus 1 is just 999. Okay, e to the minus 1000 kt. And now the nice thing here is that all of these have that k in there, so we don't need it. Divide through by k. And here's half the battle. Okay, so this is the solution that models the scenario that we have now. What we need to do, knowing that we're interested in finding out how many are infected 50 days later, we got to figure out this constant. And they did tell us that 6 days, or no, I misspoke. We want to figure out how many are infected 6 days later. We know that 4 days later, 50 are infected. So I'm going to plug in 50 and find the constant. And that was 4 days later, so this will be minus 4,000K. And if you have calculators, you might want to help me out here, because I don't have it worked out completely. So to find the constant, we can divide by 50. That'll make things a little nicer. So we get 20, and then 1 plus 999 e to the minus 4,000K. So 999 e to the minus 4,000K is going to equal 19. E to the minus 4,000K equals 19 over 999. Take the natural log of both sides. Constant is natural log of 19 over 999 divided by negative 4,000. I'd recommend storing that in the calculator, perhaps. What is that approximately? Anybody have that? Should be pretty small. 9.91 times 10 to the minus 4. So 0.000991 or so. Okay. Now that you have that, maybe you store this on the calculator, go back. We want to figure out what the population is that it's infected 6 days later. So go back all the way to your model right up here. 1,000, 1 plus 999, e to the minus 1,000, and then maybe you store that value in there, multiply it by 6 in the exponent there, and anybody have that? Nobody? What is it? Oh, this should be 1,000. I thought you were telling me the answer. I was like, what are you talking about?
I got 276.
Thanks, David. About 276? Okay. Anybody else confirm that? Okay. So about 276 students. And again, this is a great model for this kind of scenario because, I mean, if you're talking about a school or a population that has 1,000, I mean, at some point that rate at which students get infected is going to start to slow down a little bit once most of the population is infected. Okay, so, all right. What time is it? 7:45. Good. Any questions on this? This is probably the most important model in 3.3, so make sure that you're comfortable with the logistic growth and the solution for it. Again, either you learn this so that when you write a model, you can identify what's what and plug everything in. Saves you a couple minutes. Or, you know, you can go back and do the solution for the equation from the beginning and then, you know, do all that stuff. Your choice. Okay. We did that. We can probably talk a little bit about another model that's pretty interesting. A little setup for escape velocity. So maybe we have a rocket. Let's say this is the Earth. Let's say the radius of the Earth is capital R. Let's say the rocket is close to the Earth, but a little bit out there. Let's say that that's Y. And here it is a little bit above the Earth. And right here we have some initial velocity. And then after, we have the velocity after fuel burnout. I guess the question here is, after the fuel, I mean, this is what you'd have to know if you're going to the moon or launching into space. Eventually your fuel is going to burn out. You want to know if you're going to be able to actually leave and go where you need to go or not. Okay, so model for this. We have a differential equation right at that burnout point. Which is force, which is ma, equals, what's the universal law? Universal law of gravitation. Okay, I have it as constant, small mass, big mass, and then radius from the center of the big mass, right? In this case, that would be y. If you divide through by m, little m anyway, and we use a, which is acceleration, we can put in a differential here, second order, which would be d squared y dt squared equals minus k capital M over y squared. Okay. All right, so now to find the constant, we can kind of work with that fact that y is going to be close enough to r that a is going to be approximately minus g, which if we're in feet, 32 feet per second squared. If we're doing meters, negative or 9.8 meters per second squared. But the idea is that we're not far enough here that we're going to differ too much from the gravitational pull of the Earth, so we're going to work with this assumption. And now if we plug this in, we get d squared y over dt squared actually, hold on one second. Just getting ahead of myself. Going back to this model, minus k, little m, big M, over y squared, minus mg. So we're using the same model we did before to kind of find the constant. Little m's cancel, negatives cancel, and we get that the constant is going to be g r, since y is approximately r, squared, and then we're going to divide by big mass, which is the mass of the Earth. All right, and now we can go ahead and plug this into the differential equation. So k, we have negative times gr squared over big M times big M over y squared. Big M's cancel. We get d squared y over dt squared, which is equal to minus gr squared over y squared. Okay. So obviously we haven't really talked about second order equations yet. So there's got to be a way that we can somehow make this first order, maybe cheat a little bit, and there is. How else could we write this besides d squared y over dt squared? But then the differential's gone, right? dv dt, good. So let's change this to dv dt. And now, here's the trick. If we do the chain rule, because we're obviously interested in how this is related to y, we have that dv dt is going to be dv dy times dy dt. Okay, and again, now, this part is what? dy dt is another name for what? V. So we have dv dt equals v times dv dy. So we'll plug that in. So dv dt we're replacing with v times dv dy, which is minus g over r squared over y squared. And now we can separate. So we have v dv multiplied by dy, so we get minus gr squared over y squared times dy. Integrate both sides. From here it should be pretty automatic. 1/2 v squared equals, this becomes, good, multiply through by 2, let's say, so we get v squared equals 2g r squared over y plus some new constant c1, not that we need to know what it is, but it's equal to 2 times c. Alright, so now at burnout, what's the velocity there? That's when we start keeping track. What was the assumption up here? Velocity was just initial velocity, v0, right? So, plug that in. So we get v0 squared equals 2g r squared over r plus c1. So c1 is going to be v0 squared minus g r. So I'm replacing r with, or y with r. And now if we plug this in back to the model, this is going to help you with the homework. This is pretty much what you need to know going in. Velocity squared is going to be 2g over, or times r squared over y minus 2gr plus v0 squared. Okay, so this model represents the velocity. Here's the escape velocity. Okay. And you'll deal with this a little bit in the homework, trying to figure out what that needs to look like, and you'll go through a few scenarios. Escape velocity of the Earth, escape velocity of the Moon, pretty much anywhere if you want to.